Let's continue. So here now we already have all the components that we have in the magnetostatics problem. So just like the triangles for the electrostatics problem, we also have a triangle in the magnetostatics problem. So here there we have the magnetic field B, we have a source current J, and we have a vector potential A. So in the very beginning, we discussed how to calculate the B field from a source current by this J cross separation vector, the Biot-Savart law, and we also know that the Maxwell's equations tell us that the relationship between the del cross B and so the Biot-Savart law and the Maxwell's equations can help us go back forward between the J and B. And today we also introduced a new quantity called the vector potential, and just like the case in the E field, we can solve the Poisson's equation to get the A, and or equivalently, the A is can be written down as the expression over here, by integrating over all this source current in the volume, and finally the B and the A's are connected also by this definition of this vector field. So del cross A must be B, and because we are in the Coulomb gauge, the del dot A equals to 0. So you have to be clear that in the magnetostatics, the expressions are simple because we are working in the Coulomb gauge. So without the Coulomb gauge, this expression might be slightly more complicated. And likewise, we can also talk about the boundary conditions for the magnetic field. So to get a sense of the boundary conditions, we do the same trick as what we have done for this electric field. So say that we are interested in the perpendicular direction of the magnetic field. We can simply apply a Gaussian surface, such as this pillbox. So here this is a small height, and if we look at the surface integral, so the B dot this area has to be 0 because the del dot B is 0, and that's by definition. And so if we apply this Gauss law, and we can immediately tell that the magnetic penetrating above the surface and penetrating below the surface must exactly be 0. So the B must be continuous. Otherwise, there must be a source. So because there is no magnetic monopole, so the B here perpendicular direction must be continuous. And now if we want to get the parallel direction magnetic field, we can apply this Amperian loop, such as the loop over here. So we can apply the loop such that it's close to the surface, and the loop also has to be small in the height. And if we determine this, if we determine the loop integral, here this magnetic field along this the line of the loop must be equal to the current enclosed by the loop. And the current enclosed by this loop is this k times the length of this loop. So on the I enclosed is equal to KL, and you can always check by dimensionality that if this is correct. So the K is in units of current divided by the K should be in units of current divided by length, and the J should be in units of current divided by length square. So here, now if you apply this loop, you will immediately see that the B field above the surface and the B field below the surface, the difference of the two must be mu naught K. So here for the B field, it's continuous in the perpendicular direction, but it's discontinuous in the parallel direction. And if you still remember correctly, for the E field, it's discontinuous in the perpendicular direction, and it's continuous in the parallel direction. So it's just the opposite here. So you can also if write down this here. I also want to note that the here on the right hand side, the I enclosed can be written down as K times L instead of K times L and times the angle, is because here the Amperian loop is perpendicular to the current. So in principle, this K times L should be written down as K times L sine theta, where theta is, or cosine theta, where this cosine theta is the direction between the surface and the Amperian surface and the current. And this cosine theta angle is also you can also re-express this expression by this K cross the n hat, where this n hat is the direction of this surface. So here the direction of this Amperian loop is different from the direction of the surface. So to transform to that, then you have to use the cross product. You can prove that this is correct if you take account into the angles correctly. And also we can calculate the vector potentials. So if you remember, we also did a similar calculation for the scalar potential in the electrostatic problem. So the scalar potential, I believe, is continuous everywhere, and the derivative is discontinuous in the normal direction. And here it's similar that the vector potential is continuous across any boundaries. And to get y, we can simply work out the expression by applying the Gaussian pillbox surface. So if we apply a Gaussian pillbox surface, because the del dot A is equal to 0, then we do the exact same analysis that guarantees that the normal component is continuous. And now to get the parallel component is also continuous, we need to use the del cross A term. So for this del cross A terms, we have to be careful in the sense that del cross A is not exactly 0, and the del cross A is actually gives the magnetic field. So if you apply the Stokes theorem, the A field along this along a loop is actually related to this B dot the A field, B dot the surface, and that gives the flux. But we can always choose a loop that's infinitely small. So the flux through this Amperian loop of the vanishing thickness is also 0. So in the end, the vector potential must be continuous everywhere across this surface. However, if you do the math correctly, you will see that because del cross A equals B, and the B is discontinuous in the parallel direction. So under this, there is a del cross A here. So the del cross A must also be discontinuous in the parallel direction, and it translates to that the normal derivative of this A field is discontinuous in the direction of this current. So lastly, what I want to talk about is the multiple expansion of the vector potential. So we just use the identity of the generating function here that we see. So here this 1 over separation vector can be really exactly be expressed as this expression on the right hand side, and here this r prime is the coordinate of the source, and r is the observation point, and the cosine alpha is the angle between r and r prime. Because we can I think I didn't write this here. So because A field here J over. So we simply use the expression here and plug in this 1 over separation vector, and from this expression we will do the exact same step as how we express this multiple expansion for the scalar field, and then that will give us the multiple expansion for the vector field. So if you plug in this 1 over separation vector, that will give us exactly the expression over here. So now we can assign each term with physical meanings. So if I explicitly write down the right hand side, what we have should be should be the first term, where this is a monopole term because it's proportional to 1 over r, and the second term should be a dipole term, and the third term should be a quadrupole term. And so what's different from the electric potential is that here for the magnetic monopole, the integral is integrating over dl prime, and that's because we are always considering some current loops, and then this for a loop of current, the I can really be pulled out of the integral, and so here what's inside here is simply a line closed loop integral. This closed loop integral must be always exactly 0. So that's because there is no magnetic monopole, right? So in the multiple expansion for the magnetic potential, the first term is always 0. So the leading order term actually becomes the magnetic dipole term, and because the magnetic dipole term is the leading term, and similar to the analysis that we have done to the electric multiple expansion, the leading order term should be independent of the choice of the coordinate. So the definition of a magnetic dipole should also be independent of the choice of the coordinate. So let's try to look carefully about what is the magnetic dipole. So the magnetic dipole can be written down here. This is simply the P1 cosine alpha. And now the cosine alpha can be written down as the r hat dot r prime hat. So we can rewrite the expression here, and the way that we try to do this is to pull this coordinate r out of the integral, so we can have exactly a term that is independent of this that is independent of this integral, and hopefully that gives us the dipole. And you right now you have to believe me that the integral on the right can actually be written the term like this. So here the r vector is being pulled out of the integral, because this integral is an integration over the r prime, and somehow you have to change this dot product to a cross product. So in the end, what we see is the integral here can actually be the r dependence can be pulled out, and you have to cross this r by area, where this area actually have some okay, that is a vector.
Can I ask, because when we consider the potential, we write it as non-dipole expansion, then there is a closed loop integral of the L prime vector. Can I ask, what is the direction there? Because I cannot interpret it if it is a closed loop integral.
You mean the direction? So here is the loop integral is always 0, right? So you don't have to worry about the. So this the entire thing is a scalar. Let me see. Oh, it's so it's 0 anyway. Like it's a vector, but it's a 0 vector. Okay, so So now we pull this r out of the integral, and then we can rewrite the dipole term similar to this electrical dipole term, and except that we have to define m, that is that's the m here is the magnetic dipole, and the definition is the current times the integration of the area. And if we have that definition, then the magnetic dipole is simply the m cross r hat. So I also want to mention that here this A is actually something, the integration here is, you have to be careful in the sense that here this area is a vector. So if you say that we have a current loop that is exactly flat, then the size of this the size of the area determines the total area, and the direction of this area gives the direction of the area over here. But be careful that say we have a three-dimensional area where the area can curve in the space, then you have to really add up each flat areas with directions correctly. So in general case, this the integral of this area does not give us the area of this surface. So I'll give an example. Say that we have a current loop like this, and if we want to evaluate the monopole, so the m, so the m is in principle the I times the a vector, right? And now if we apply this to this surface, we really need to separate the surface into two terms. One is on the left, one is on the right. Here, even though here in the middle there is no current, once we separate them, we can add a current to one side and the current to the other side. And now, because these two surfaces are flat, then we can calculate the A accordingly easily. So here A for the M on the left is the W squared times I times along the y direction, and M on the right hand side is I times W squared along the z direction. So the total M should be along the direction of here. So and you also need to note that here the direction of the surface is also important. So you have to be aware that the direction is all along the z-axis instead of the minus z-axis. So the way to determine the direction of this surface is to use the right hand rule. So you can use the thumb to be the direction of the surface, and the four fingers crossing is the along the edge current. So here on the right hand side, it should be going pointing upwards, and for this loop here is pointing to the right. So one is y hat, one is z hat, and it's not minus z and not minus y. Okay, so we haven't proved this identity yet. But before we go to that, let's take another look at the dipole expression. So now similar to the electric dipole, we can also define a perfect magnetic dipole by shrinking the size of the dipole into zero. So this is equivalent to observing the dipole very far away to the object. So in this case, we can work out the exact expression for the A field of the dipole, and if you go through the steps, you should be able to see that the A field of the dipole, if you if you go through the calculation, it's easy if you align the dipole along the direction of the z-axis, and now you can define the theta as being the direction, the angle between the your coordinate and the magnetic dipole direction m, and you can also define the phi accordingly. So if you work out the A field for the dipole, it's along the phi direction, and you can also work out the magnetic field, that is del cross A. And if you write down this in a coordinate-free term, the magnetic dipole looks actually something similar to electric dipole. So if you recall the expression for the electric dipole, you simply need to replace the P by you replace the M by P, and then this actually gives you the exact same expression as the electric dipole. So from this point of view, the electric dipole is really similar to the magnetic dipole. But what you have to pay attention is that for a physical magnetic dipole, that is that can be represented by a loop of current, and the physical electric dipole that can be represented by 2-point charge. The near field is quite different. So even though the two produce the exact same form of the far field expression, when you go close to the physical dipoles, the magnetic dipole and the electric dipole gives you quite different expressions. Okay, so let's go back to try to look at why this expression is correct. So to convince you that this is the case, let me see. First, what we can do is, so here on the left hand side is a linear integral, and on the right hand side is surface integral. So the first step is we can do something using the Stokes theorem. So the Stokes theorem can claim that a line integral across a closed loop can be replaced by a surface integral and with a del cross. And you have to be careful. So is what I'm writing correct over here? So actually, what I write here is not entirely correct. So do you know what I'm talking about? Why I'm not correct here? So the thing that I omit here is actually a prime over here, because be careful that because this integral is with respect to this prime coordinate. So when you apply the Stokes theorem, the del is also applying to the prime coordinate instead of the original r coordinate. And now we can write out explicitly the del prime operations onto this dot product. We get think hat dot so so we get a in the end we can get a single term that's applying on the del prime the del prime operator only on the r prime. And now we can write out explicitly the expression for here. We can try to this expression is actually not intuitive, and because here there is a del operator, but the del operator is only applying to the right. So we have to it's best to write out this explicitly in terms of Cartesian coordinate. So the r hat is simply the square root of 3x hat plus y hat plus z hat, and we dot the x hat partial x prime partial y hat partial y prime. So then we can combine the first two terms, and we get now if we do the derivatives of this right on the right hand side, we can see that the partial x is only along the x direction, partial y is only along the y direction, and so we get back x plus y plus c and cross dA. So that is indeed the r cross dA, which is sorry, I think I missed the minus sign from the very beginning. So we have a bit of time left, and so we calculated the vector field for the rotating shell. We can also calculate the magnetic dipole moment of this rotating shell as well. So now if we to calculate the magnetic dipole moment, what we have to do is to get the m equals I integrating over the dA. So to get the dipole moment, we can separate the shells into different strips. Say that instead of calculating the entire thing at once, we can get a strip at a time, and now here we take the each theta piece at once, and so the charge along this strip of ring is equal to the charge density times the area. So the area of this strip of ring should be 2 pi r times the radius of the area. So that should be sine theta, and so it should be times r d theta. Now this amount of charge is actually moving in time, and what it takes to finish one loop is 2 pi over omega. So so here the frequency, the dt equals to 2 pi over omega. So here now what we have is the current must be equal to, by definition, is dq dt, and so for each ring strip, the current is sigma omega r squared sine theta d theta. Now the total area of this ring is pi r sine theta squared, because here this angle is so the radius here is r sine theta, and then the infinitesimal dm equals IDA, which is del omega pi r fourth sine theta cube d theta, and what we have is the m should be integrating over all the dm, and in the end it should be going. So you can try to figure out the derivation on this example by yourself. So so you are supposed to be able to calculate the the magnetic dipole for a given current distribution like this, and then from the magnetic monopole, from the magnetic dipole, you can get the far field expression from the using the multiple expression. So try to finish this example at your own pace, and to see if you are familiar with how to do the integrals here, because the integral here is actually tricky in the sense that the area is directional, and you have to take this account explicitly, otherwise you might make some mistakes. Okay, so now we've already completely finished chapter 5, right? And so then this means that our description about the magnetostatistics is already complete in the vacuum. So in the next lecture, we will start the chapter 6, which discusses the magnetic field and the interaction with some media. So just like what we discussed about the electric field in media. Okay.